on the surface, their cost is a big issue. And their cost, the main thing that affects their cost is the design cost. The design cost in turn affects the development cost. The development cost in turn gets accounted towards the operating costs. Secondly, this is a vehicle which is a wide variety of types, so you can pick up from different types and you can test the different computational intelligence algorithms to see which works best for which kind of flight vehicles. So therefore, we specifically took up the SOVs as a case study. Then we need to remember here that all flight vehicle designs go through what is called as the ICASE design principle, which is based on a large empirical data. So doing a CI on flight vehicle design will actually be assisting the designer in overcoming this collection of empirical data and then doing a solution which is fast and frugal, cost effective, and time efficient as well. Okay, so there are many ways in which CI can be implemented onto the flight vehicle design. And what we have done is we've brought together basically two approaches. The first approach is where we have worked on predictive design parameters while working on baseline configurations, as we can see. That means that we are starting from some design baseline. And this approach is being used in the form of an expert system whose objective is to maximize conformance with the baseline while minimizing the number of inputs required to achieve the conformance. The second scheme that we are going to work on, in fact, I'm presenting here, is which we have been applying for flight vehicles without baselines. And these are typical flight vehicles like futuristic systems which do not have any legacy data at this moment. This approach relies on something called as heuristic data and intelligent classification schemes. And the overall objective is to maximize the fidelity of the results while minimizing the computational effort. So the two schemes have two different objectives, but the ultimate idea is to get to a flight vehicle design. Now, we at this stage cannot come to a complete flight vehicle design because of the number of variables involved and, of course, the limited computing powers. So we've chosen for all these cases some of the parameters which we call as the initiation parameters for the design process. All right. So conceptually, an expert system, which is the heart and the soul of this project, is based on cognition, as I've already mentioned, and it uses human evolutionary judgment, the ability to learn and recall the learned experience, and then combine the knowledge and the experience together in what is called as modern human thinking or cognition. And this cognition, therefore, will form the basis of creating a human thinking-like behavior in choosing the design parameters for our flight vehicle systems. Right, so that brings us to the research concept. Now, what we've done is, I've just tried to put everything together in a short while. So, putting these things together, our research on CI is based on carrying out SOV design. SOV, of course, stands for suborbital vehicles, and is aimed at developing cost and time efficient solutions for evolving the configuration parameters of aerospace systems using what I will be referring as simple as possible input. Simple as possible means I'm going to do this design process with minimal possible input that a customer can give you, and you can be able to derive or extract some reasonable number of design parameters for your flight vehicles. And those parameters can be fed into your decision support system that can be used by the customer or your sponsor, or it can be then fed into your classical design process to initiate the classical design process in situ. Okay, conceptually, on a one-to-one basis, we believe that CI will supplement at this stage, but one day it's going to completely replace the classical design method as the maturation of the expert system and heuristics take place. And in the process, we're going to maximize the number of design parameter outputs while continuously decreasing the number of inputs required for a particular aerospace vehicle design. Okay, so let's look at this basic scheme, how the methodology that we have planned works on. The figure on the side is representing how a classical design scheme of a SOV works in its simplest possible form. As one can see, the design process will start by using large number of design variables on the blue side. The design variables that's going to go through some, correct some design constraints, We're going to take into account the educated assumptions about the design for which we don't have any data, and then a lot of trade study has to go in. This is a long process, and once this long process is done, then the process of the actual classical design scheme starts, where we establish the baseline, then we carry out the aerodynamics, the propulsion, weight, trajectory, performance studies, and then after all the decision has gone through, we take into account some figure of merit to see whether we have achieved what we were looking for. And if it is achieved, then we will go for the sizing process, and then the iteration cycle begins all over again. And so it's an iterative process, goes again and again and again. Now, imagine what we propose here is that if this initial constraint to the design, if this initial portion of the data collection and legacy data was replaced by minimal input, or the customer only has to feed in just 2 or 3 or 4 variables, and the big data of legacy designs is going to do the mapping of the input to the output, and the machine is already pre-trained. The outcome would be then a design process. The outcome would be actually predicted design parameters, and these predicted design parameters will be simultaneously fed to all the aerodynamics, the propulsion, the structure, and all those modules, and this will shorten. This is really, really going to shorten the design process time for our aerospace vehicle system. And of course, in the process, it's going to cut down the cost of development and so the cost of operation in the due course of time. This is the whole idea of what we're doing. Okay. In this process, what we've done is we've split the SOV vehicles first on the basis of their legacy parameters. And for the large, for example, for the large suborbital vehicles such as launch vehicles and some ballistic missiles, these legacy parameters were going to fall primarily into what is called as a discrete data domain. So there is well-defined data between different vehicles. And hence their mapping function was obtainable using one of the neural networks families, as Dr. Thomas also mentioned. The second type of the vehicles that we've chosen are actually small tactical vehicles like your air-to-air missiles, air-to-ground missiles, surface-to-air missiles, surface-to-short and surface-to-surface missiles. Now these systems have very specific problem. They have overlapping parameters, and as a result, their knowledge system is very large. But the problem is that the mapping function is very tough as far as neural networks is concerned. Therefore, adaptive neurofuzzy is one of the solutions. As mentioned, we can have many inputs and specifically take out one particular parameter from a set of large number of inputs. The third kind was the most complicated, which is the non-legacy parameters design. It's based, which is called as the heuristic domain system. And this is usually used for futuristic suborbital systems such as the hypersonic cruise vehicle, the two-stage to-orbit vehicle, the single-stage to-orbit vehicles, and all those things that are still coming up as time passes. And for these, we have undefined variables, we have little or no legacy data, so we had to build up a knowledge base, and for that building up, we needed a knowledge base using heuristics, and the heuristics has to be combined with computational intelligence. So we call it the heuristic intelligence network, and that would create the kind of legacy data that would be needed for the design process, and then from there we would apply different type of classification schemes to select which is the best one. So these are the 3 classifications, and to apply these classifications we have built 3 modules. The N2SM deals with the mapping of the input to the output for the large systems, and in this case we are using multi-layered feed-forward networks of ANN. And in this case, we're going to have artificial intelligence deployed, which is computational intelligence, to adjust the weights and biases without human input. So those weights and biases, the number of hidden layers are going to be adjusted automatically for every design variable. And then the second one is the ATMM module. Sorry for the ATTM, it is ATMM module. And this is mapping the parametric input to the output for for technical level systems. And for that, we have selected, after a lot of effort, the Takagi-Sugino model. And within the Takagi-Sugino model is going to run inside the adaptive neurofuzzy inference system. And it's also going to have a feed-forward network. The last one is actually the toughest of all, which is the one without any legacy data. And for that, we have extracted using inverse design methods. First of all, we use customer input to go back and decide what kind of likely parameters are going to be there. So we use an inverse design methods, integrate that with heuristic optimizers, and then intelligent classifiers. Combined together, this is called as an optimizer classifier cyclic method. And this is a method that we have developed in this process, and this will be applicable for all the futuristic systems. Right. So, in order to apply this entire concept at level 0, which is the concept level design of the flight vehicle, where lesser number of variables can be handled at this stage.
What we did was we created a black box first. And the black box, we have the cognitive heuristic work analysis method put into the framework inputs, and we get the qualified system design outputs. And now what is happening inside the black box is we are integrating the aerothermodynamic compression systems database with the mass model database of a two-stage or two-orbit vehicle. When they combine together, the mapping function produces surrogates of configuration. Those surrogates of configuration are used first as the initial classifier to take out one baseline configuration, which is called as an anchor configuration. Now, based on that anchor configuration, they are going to apply the heuristic optimizers. And once the set of results are produced, then what we're going to do is those set of results will be passed to an intelligent classifier. That intelligent classifier helps us find out which is the most intelligent solution obtainable for this particular set of input parameters coming from the user. Now, this whole thing is working inside an architecture, and this architecture is of course part of the CVEX program. On the left hand side, this is where we calculate the initial part. The initial part is where we have selected the first set of baseline results. These baseline results are the first. And in this optimizer classifier cyclic method, for example, we have taken up 19 or 20 or 15 variables, as number of variables we are looking at. And they are going to go through every iteration, they're going to go through a classifier, which is in this case a support vector machine, until all three goods are attained, which means 3 times the results are obtained as a good configuration. This will then be considered as an OCC's baseline anchor configuration. This anchor configuration can now be passed on to the, after the classifier has been done, is going to pass to the cyclic method, which is a non-cyclic method, which is your classical design scheme. So in your typical classical scheme, this whole process was going through cycles and cycles, putting a load on your computing machine. Now only one configuration is generated, that is intelligently classified and passed into your classical scheme, and that makes a very fast process, just as we mentioned at the beginning of my talk. So, but I'm just taking out some results. These are results for the aerothermodynamics part, these are for the geometric parts, and these are some for the mass modeling part. And we started off with a totally unknown information with that is Mach 6.8, and it should be able to carry 500 kilograms into the orbit. And the orbit we chose was about 250 kilometers. The outcome is that we get this is extracted, this baseline configuration is extracted based on the HI2D. Then this got intelligently optimized, and we have this user. Now when this configuration was put in, we got this geometry. When this configuration was integrated with the CAD model, the geometry is optimized and looks really like a space plane as these things appear over the horizon once we have these new hypersonic tests taking place every now and then. So this is a hypersonic 4-particulate configuration optimized for a particular mass model configuration. I'm going to move to the next module, which is the N2SM module for my ICBM and launch vehicle systems. And here we've designed an expert system. For an expert system, we used a very large knowledge base, and this knowledge base was actually mapped together with those list of inference engines that was also discussed by Dr. Tamir. And we went through a long machine learning process. It took about 3 to 4 months for the machine learning to take place. Now the user can just plug in his into our GUI and input, and you will get your numeric. This is as simple as an expert system gets. Now, how does it happen is, the first step is always at a level 0. We're going to choose the number of variables that we can handle. And these variables will be dependent on the fact that what information can you get from archival data, free source data, books, magazines and all that. So very tricky decision. Any extra data is going to act either as an outlier or it's going to be blank, a lot of nulls in there. So once these have been chosen, the next step is actually putting it in, this data is read into the feed-forward network. It has to be trained here. Now, where the feed-forward network is usually fails is it's not able to put back the errors. So, a back propagation network has to be written for this thing. So, back propagation puts the error back here, and this is read back, and it is trained of the long cycle. So, as I mentioned, on a normal computing machine, it took us about 3 to 4 months, even more, about 6 months to train this, and we train it in a multi-layered feed-forward network with back propagation. The outcome because the weights and biases are a big issue. How to adjust those weights and biases? We can do it manually in a typical MATLAB, but this is not what the purpose is. So the entire intelligent scheme works on calculating for every variable what would be the number of hidden layers that should be used, what should be the weights and what should be the biases. So this scheme here shows you that for a vehicle stage, for example, calculating an integer requires only optimally 3 hidden neurons. But for a CP requires about 10 because CP is a decimal place. So CP, for example, requires 1 decimal place, you need about 10 neurons to that. For a length of the vehicle, that's about 35 neurons. So as you can see, as the number of decimal places or the degree of the margin of error is reducing and the number of decimal places increases, so automatically the intelligent scheme is picking up more and more adjustable number of neurons, and this is different for every variable. In a normal ANN scheme, you will not be doing that. You will just using one fixed value, for example, just put 3 neurons, 3 hidden neurons and just get all the results. So you will never know that those results are good or bad. Here the results are being adjusted every time because of the intelligent classifier. So this is our basically, for example, the GUI, and you see that the only 2 inputs required from the user are, for example, the vehicle range and the payload. And you cannot design any aerospace vehicle just based on these 2 inputs. But here we are extracting parameters including this configuration, possible configuration for our flight vehicle that can be obtained from this solution. So this is a result of many results were produced, and this is R36M. For example, we took out the parameters of R36M. We fed those parameters as a user input. 10,500 range, 1500 km is the payload. And these are the predicted parameters. The results are 10,000. You get your apogee height, you get the number of stages, you get all your parameters, and this is the actual results. So as you can see, that where the integers are involved, the error is almost 0. And only where a bit of decimal places are involved, the error slightly rises. So if we can go through a lot of training processes and improve the accuracy, so even this part is also going to calm down the few variables which are left. So there were about 19 or 20 design variables, and now these are all, you can see these are geometric variables, they are propulsion variables, some of them were aerodynamic variables, so they can all be fed directly into their starting module, and you don't have to go through your recursive process, basic recursive process. Right, so this is your conformance plot, this is the performance plot. This shows that 94% of conformance was achieved basically on the during the training process, the testing process, and the validation process as well. Now, the third module we do was the ATMM, which was for the vehicles which had a problem, about the flying parameters. Now, in this case, for example, we see this is a very critical area because the number of systems are large, and there's an overlap here. For example, the shortest range of a long-range missile overlaps with the longest range of the short-range missile. So there's an overlap region. So there are many such parameters where the tactical systems actually overlap in their parameters. For example, the length of the warhead versus the length of the nose versus the size of the parameter. So when this happens, we have to go into the neurofuzzy domain. And in the neurofuzzy domain, we create membership grades, and those membership grades are adjusted as per some mathematical rules are created, and those mathematical rules have to follow. So for every individual parameter, this range and payload goes in, and you get one set of parameter output which is bigger. So it's many to one mapping. And unlike neural networks, where one neural network was able to handle many variables, here for every variable we have to run this MFIS individually. So it's again a recursive process. Okay, so but this architecture had a problem. MFIS is very stable, but it does not work for tactical missile flight. Any students can try that out. So this had to be enhanced, and the enhancement was that the input was passed first through simultaneously to the learning process, the MFIS learning process, and also to an intelligent classifier. So based on the same set of inputs, we had trained the classifier to first be able to classify the tactical system into their own specific textual category. So the text data output was generated for surface to air, surface, air to ground, air to air missile. Now when this category was passed on to the MFIS was able to generate the results much more stable, much more conformal for, let's say, these listed parameters. So that means that MFIS cannot directly be used, and I have a very strong test case in this area. And so the pre-classification of AMPHIS is something that works very well if you are doing an aerospace vehicle design, but not without a pre-classification scheme. This is a quick, can you just run this movie, please? Yeah, that's it, finished, thank you. This is the total time it takes. So we put in the range, we put in the payload, and the computing starts, and we have the pre-classified AMPHIS, and the membership takes place, and then we have the rule basis. The rules are getting adjusted, and we get the rules adjusted also on the basis of our CI. And we have the response services generated, and it takes less than a minute's time, I guess. It actually also classifies, as you can see, this is also classified that for this system, what would be the possible weapon system or the weapon that you can get, along with the total results. And that is all it takes. And now you can start your design process without running through your process of collecting your information and data and all that stuff, which is a very, very fast way. Okay, so we just ran these for many systems, and this is another comparison of the results. We took out with the third column actually lists the actual parameters, and the second column lists the predicted parameters. We see that the two predictions were very correct as far as the type of the system was concerned. The length parameters, the diameters, the geometric parameters were all in conformance. The performance parameters were also in reasonable conformance, and all the other parameters, including, we also tried out how the guidance system was. So we had a reasonable conformance. The numeric prediction worked on three basic. It found out that we should have beam riders, we should have an IR homing. The actual one had a beam rider, an IR homing, and a C3 additional module to it, which of course it could run, but it was still very, very reasonable to start a design process. You can always make an iterative phase in the along. Right. So what we've done here is, in summary, if I'm going to put everything together, we took a design process which was very, very classical. As we see here, we had separate modules for configuration, geometry, aerodynamics, ramjet, rocket, flight, and what we've done is we have reduced its effort by introducing computational intelligence applications, and those applications have initialized the design parameters. And those initialized design parameters are individually fed to each of these modules, and now instead of having to go through and collecting all the initial data, you can just straight away have enough input to start these calculations straight away without going through your trade studies and all that stuff. I had to run through because I thought the time was running out. So I would conclude here by saying that we have successfully demonstrated a carrier vehicle expert systems program. It's a concept program, and it uses big data analysis applied specifically to aerospace vehicle design. And I believe that we've done it's showing us very promising results. The CVX has exhibited the ability to predict preliminary, or what we call as the initialization design parameters for an efficient SOV design process. What we also found out in the process is the concept employed here was successfully applied to extract parameters for 3 different types of SOVs. We did it separately for a large ballistic missiles, the small, the tactical ones, and then the futuristic hypersonic vehicles. And it was pretty promising, the results. And in the process, it was determined that for discrete legacy database systems, discrete legacy-based data systems, the neural networks families was best suited. Whereas for the fuzzy systems, the AMPHIS had to be adjusted, modified, enhanced. And for systems where there was no legacy data, the CI was still possible by introducing heuristic intelligence schemes. And then all flight vehicles that we have gone through in the process, the AMPHIS was able to, all the results were verifiable. And these results were also validated across their own original systems. And we got some very, very promising results, some of which we have already seen here. Finally, my closing word is that one can sum up by saying that computational intelligence approach, such as the CVX, what we have presented here, if and when fully developed at all levels of the flight vehicle design, will be a huge jump and a very strong assurance to a cost and time efficient method for extracting the designs of flight vehicles in future. Thank you very much.